For this example, we're going to consider the following situation. We have the triple integral over the solid b of x squared z plus y squared z dv, where b is going to be the solid contained inside the cylinder x squared plus y squared is equal to 9, and between the planes z equals 0 and z equals 5. Now, very first thing that I'd like to do is take a look at this xy trace, like we said in the last video. So we have x squared plus y squared is equal to 9. The xy trace of this is going to have a cross-section that is a circle. This will be a circle of radius 3. Now, we take a look at this and we say, is it round? And the answer is, oh yeah, that's a round boy right there. So given that it is round, we make the conversion into polar coordinates. This will be r squared is equal to 9, which simplifies as r is equal to 3. No plus or minus sign, since we can always contain r between, we can always contain r between non-negative numbers. So with that in mind, now let's take a look at the corresponding RZ trace. Now for the RZ trace, what we have established is that this cylinder lies between r equals 0 and goes out to r equals 3. So 1, 2, 3. Z equals 0 and z equals 5 in the RZ trace will look like horizontal lines. So z equals 0 would be the r-axis, and then 1, 2, 3, 4, 5. That'll be z is equal to 5. And here is r equals 3. So the region in question would be this cylindrical region right here. Question that we get to pose is this round? And I would certainly hope that by looking at this that you would ascertain, no, this is not round. So because it's not round, we are going to convert x and y into polar coordinates, but we are not going to transfer r and z into spherical coordinates. So because it is not round, we are going to use cylindrical coordinates. So let's take care of all three things that need to take place. First thing will be the bounds. For the bounds for this triple integral, we will need to bound z first. Then we'll need to bound r. Both of these can be done from the RZ trace. Theta, though, is going to have to be bounded by the XY trace. That's because r and z are visible in the RZ trace, but theta is not. So we'll go back to that as we need to. So z, we can see in the RZ trace going from top to bottom that this is going to be z is bounded below by the plane z equals 0 and above by the plane z equals 5. R, going from left to right in the RZ trace, is going to go from 0 to the radius of the cylinder that we had, which was 3. Then for theta, we go back to the XY trace, and we see that we are talking about the entire XY plane, so one full rotation. That'll be 0 to 2 pi. Now that means that we can set up our triple integral of b. Quick thing to point out here as well is that if I were to factor out a z from these two terms, I would be left with x squared plus y squared. I'm going to go ahead and do that to make our conversion into cylindrical coordinates a little bit easier. So our bounds will go from 0 to 2 pi for theta, 0 to 3 for r, 0 to 5 for z. Z stays as z. X squared plus y squared gets converted into polar coordinates. That'll be r squared. And for dv in cylindrical coordinates, that would be r, dz, dr, d theta. So that is our conversion into cylindrical coordinates. Next thing that I'd like to point out is that the integrand can be factored into a function of z times a function of r times, well, 1 for theta, and that all of our bounds are constants, which means that we can invoke Fubini's shortcut. So for theta, we're going from 0 to 2 pi of 1 d theta. We're going to multiply that by the integral from 0 to 3 of r cubed dr, the r squared that we got from the integrand and the r that we got from the Jacobian. We're also going to multiply that by the integral from 0 to 5 of z dz. So this will be theta going from 0 to 2 pi times 1/4 r to the 4th going from 0 to 3 times 1/2 of z squared going from 0 to 5. This is going to be equal to 2 pi times 1/4 of 3 to the 4th, that's 81 over 4, times 5 squared over 2. The lower bounds will wind up giving us zeros. So 81 times 25, let's see, 25 times 8 is 200, 2,000, 2,025 pi over, cancel out one of the 2's, 4. So final answer for this one, the hypervolume that we just calculated for this this solid, hypersolid, I guess, 2,025 pi all over 4.